Hello, I am Harrison Monfort, and I will be presenting Chapter 18, Sections 11 and 12 from the Organic Chemistry Brewis textbook. I will be discussing the nomenclature of disubstituted benzene and what affects its reactivity. So, naming disubstituted benzene molecules, how do we do it? Well, on the left, you can see 1,2-dichlorobenzene. The chlorine substituents are identical, so they can be labeled as dichloro. When we name these, however, we want to get the lowest possible number combination, so we put 1,2 rather than 1,6. Below that name, you can see another name, which, why have two names? Well, the top name is the systematic name, and the lower name is the more common name that scientists use regularly. So ortho simply means that the substituents are on adjacent carbons. Meta means that there's one carbon in between, and para means that there are two carbons separating them. So what do we do when we can't say dichloro or dibromo or dimethyl? Well, on the left, you can see 1-chloro-2-methylbenzene. We name them alphabetically, so chloro receives the first position and the methyl, M, receives the second position. On the right, the bromo will receive the first position, B, and the chloro, C, will receive the third position. Some substituents can change the name of the benzene ring itself, so the hydroxide group, highlighted in red, will cause it to be called phenol, and the amino group, highlighted in blue in the middle, will cause it to be called aniline. So on the left, you can see 3-iodo-phenol. So the hydroxide carbon receives the first position, and the iodo carbon receives the third position, trying to use the lowest possible number combination. On the right, you see 4-nitrophenol, which the phenol again gets the first position, and the nitro group gets the fourth carbon because either way they're the same, whichever way you go around the ring. Naming polysubstituted benzene molecules. So again, you place these substituents in alphabetical order. So 2-ethyl, 3-methyl, aniline. And again, in this case, the aniline changes the benzene to aniline. You always, again, want to get the lowest possible number combination. So on the right over here, you can see 2-chloro, 1-methyl, 4-nitrobenzene. So we assign the first position to the methyl group rather than the chloro group, because if we went that way around the ring, the nitro group would be on carbon 5 rather than carbon 4, which is not ideal. So these substituents will affect the reactivity of benzene, as it is usually a non-reactive molecule. Some of them will donate electrons, which increases its reactivity, which activates the molecule. But on the other hand, some will withdraw electrons, which decreases the reactivity, which deactivates the molecule. So, strongly activating substituents. Well, these will donate electrons by resonance, but also inductively withdraw electrons. However, the donation plays a much more significant role in the overall effect. Some examples of them are shown on the right here, such as the amino groups or hydroxide groups. But not all of them are strong. There are different categories, and there are weakly activating substituents. So alkyl groups and aryl groups, shown on the screen, will weakly activate the benzene ring. So alkyl substituents will donate electrons by hyperconjugation and also inductively withdraw them, but again, the donation is much more vital to the benzene ring. On the other hand, we can strongly deactivate substituents, which both inductively withdraw electrons and withdraw electrons by resonance. Some examples of these are shown, such as the nitrile group on the left or the nitro group in the middle. Lastly, we have the weakly deactivating substituents, which donate electrons through resonance, but also inductively withdraw electrons. And in this case, the inductive electron withdrawal is stronger than the electron donation. Thank you.